Hey everybody, Doc here. We are on day 3, Calc 1, lesson number 7, section 1-7 in the correct book, 2-3 if you have the other book. Now today we're going to go over the precise definition of the limit, and it's going to be probably a shorter lesson. Those of you that like theory and proofs, you'll like this section and you can go deeper into it if you would like. But we have a lot to cover in a short amount of time. So we're just going to go through and examine it and then move on. All right, so we looked at these before where we had the limit as x approaches 0 of this function being 1/10,000. I don't know if you remember that. It was just a day ago probably. And we had this limit and we found that it approaches 1. Now, everything that we've looked at so far has been intuitive, meaning that we've looked at it, we've logically said, well, if it is that close to that number on each side, then it has to be right. But we have had nothing that said how close is how close you should get. We say closer and closer to, but we really don't say how close should we get. So let's take a look at this example here. Here we have a piecewise function, 2x minus 1, and x does not equal 3. But when x equals 3, the result is 6. So we can look at this and say, well, intuitively we can see that if we get closer and closer to 3 on both sides, it's going to be 5. So the limit as x approaches 3 of f of x is 5. But how close does that have to be so that f of x differs from 5 by less than 0.1? Now, where did I get 0.1? I just decided to choose 0.1. You'll see later that, we might want to get a lot closer than that. We might want to say 0.01 or 0.001. So now we're going to take a look at the distance from any number to 3. The distance can be represented by the absolute value of x minus 3. This just means the distance from 3. Why 3? Again, going back, we're looking at 3 as what we're approaching. And the distance from f of x, or the function, to 5 is going to be f of x minus 5. Okay, so again, in our problem here, f of x, what we're talking about, is 2x minus 1. So we want to take a look at that. Now, we want to find a number, and now we start throwing in some Greek letters here so that we can show that we're doing something a little different with proofs. So this is delta, and we want to find a number delta such that we have this answer minus 5 smaller than 0.1. So in other words, we know that we are close to what we are looking at, closer than 0.1. Now again, this could change. You might have 0.01, 0.001, depends on how accurate you want it to be. Here again, this is our x values. We're talking about 3. So we want to see that the difference between that value that we're looking at and 3 is smaller than delta. But again, we're not going to talk about 3 exactly. We're still looking at limits, so we're not looking directly at 3. All right. So if the difference from the value that we pick, minus 3, is greater than 0, then it cannot be 3. We know that. So an equivalent formula of our problem is to find a number such that we have the answer minus 5, which is our proposed limit, our answer minus 5 less than 0.1. If our x value that we pick is positive yet smaller than our delta that we chose. Now, they point out, notice that if you have your x value, the difference between your x value that you're looking at and 3, we know it's going to be positive, so it's greater than 0. If we say it's less than, let's divide this by 2, 0.05, let's see how that affects us. Now I have my y value minus 5. I'm going to go ahead and plug in my function finally. So from up here, I take my function and plug it in and simplify it. Notice that 2 is a factor, so I'm going to factor it out. Oh, and this looks familiar. I have x minus 3. So if I take that value, x minus 3, I already said over here that it was equal to 0.05. So I'm going to plug that in. And I get 0.1. In other words, if I take my answer, minus 5, I want it to be smaller than 0.1 if my domain values are smaller than 0.05. I'm going to have to be smaller than this number to be smaller than 0.1 or 1/10. So the answer to the problem given by delta equals 0.5. That is, if x is within the distance of 500ths from 3, then f of x would be in a distance of 0.1 from 5. So we're saying you'll be close enough to say it's the limit if you're within 500ths from 3. In other words, we don't just want somebody to say, as x approaches 3. Okay, so let's just look at the number 1. That approaches 3, or number 2. That approaches 3. We want them to get really close to 3. And as I mentioned before, you can get smaller than that for more accuracy. And obviously in science, we want to be as accurate as we can. So you'll see here that we might have 0.001. We might have 0.005. We might have 0.0005, okay? We could use these numbers to show better accuracy. And any of you that has taken statistics or have done research or have read research, you know that accuracy numbers are important. And now we have to determine which one of these best suits our problem. And we consider these error tolerances. In other words, I can be within this range and still say that I'm pretty accurate. Okay, so that brings us to our point here. We had our f of x minus 5. Now we're going to introduce epsilon. Okay, epsilon is our little e. We want it to be less than little e. If, and that's just another variable, if we take our domain and it is greater than 0, meaning it's positive, less than our delta, and our delta is going to be whatever epsilon is divided by 2. This is a precise way of saying that f of x is close to 5 when x is close to 3. This statement here says that we can make the values of f of x within an arbitrary distance from epsilon, from 5, taking the values of x within a distance of the epsilon divided by 2 from 3. Okay, so in other words, this whole thing that we just took a look at here basically is saying we want to make sure that when somebody is giving us a limit, that they are getting as close as tolerant that we can say we'll accept that limit for that number. Okay, let's look a little further. Here's a picture of what I just talked about. Some of us learn better by pictures. And I have my 3 here, and here I have subtracting delta a little bit less than 3, adding delta a little bit more than 3. And here I have 5, and I have subtracting epsilon a little bit less than 5, a little bit more than 5. So I'm looking at this range in here. I'm saying if we pick something within this range, then we then can say that we're confident of our limit. So the definition of a limit looks similar to before. We say the limit of f of x as x approaches a is L. For every number that epsilon is greater than 0, there is a delta greater than 0 such that our domain number minus the a that we're looking at has to be between 0 and that number delta, and our range, our result, minus our limit has to be less than epsilon for it to be valid. So again, we're basically saying that we want this to be accurate. We don't want somebody just picking a number over here 5 and saying we're close enough to 3 that we can find the limit, and the limit's going to be some number up here. We want to make sure that when we're doing limits that we are actually examining as close as we can examine to the point. Okay, here's another example over here just using a number line. So this number line says here's a, and this is just again another way to describe it. I have my a value. I'm going to subtract my delta from a. I'm going to add my delta from a. So I have this range that's acceptable for me to use in my domain. And as a result, the range will also be the limit a little bit less than epsilon, a limit a little bit greater than epsilon right here, okay? Now, the graph, again, what we talked about before, again, just another way to look at it. Here we have a graph right here. I'm talking about my limit. I have a little bit more than the limit, a little bit less than the limit. Now let's take our domain, have a little bit less than the domain, a little bit more than a domain, and the intersection of these two will give me that area that's acceptable for me to examine when finding the limit. Let's take a look at an example. Let's look at example 2. Here I have the limit of 4x minus 5, and I'm saying that I want to prove that that's equal to 7. Okay? Here's my line. It's a line. Here's my limit as x approaches 3, and here's, or my domain as x approaches 3, and then here's my limit, 7. So I want to look at an area a little bit before 3, a little bit after 3, and that value should give me an area a little bit more than 7 or a little bit less than 7, but within my range of delta and epsilon that I chose. So again, x minus 3 just means the difference between the number that I'm looking at for a domain. I want that number to be less than the delta that I chose, but it has to be positive. And then my range value minus the limit has to be less than the epsilon that I chose. So let's take a look at this. We're going to simplify this here. And when I simplify this, I'll make 4x minus 12. I can pull that 4 out and I see I have x minus 3. So I pull the 4 outside and I know that now I have 4 times my difference of my number minus 3. So therefore we want delta to be our difference, again, positive and less than delta, then 4 times x minus 3 has to be less than epsilon. So I'm going to solve this and get this by itself. So I'm looking at epsilon divided by 4. This suggests we should choose epsilon divided by 4. Okay? So I take a look, move down here, and I have, again, here's my 4x minus 5 minus my limit. And I factored out my 4, and 4 times delta equals epsilon over 4, and that will equal my E value. So that will tell me by the definition that limit of x approaches 3 of 4x minus 5 is in fact equal to 7 by using the limit laws. Actually using the accurate definition of limit. Now, we do still have left-handed, right-handed limits. Same kind of thing. We have as it approaches from the left and as it approaches from the right. We have a minus our delta. X has to be greater than that, but less than our value of a. And then we have our range minus our limit, which is also less than epsilon. Similarly, down here, when we have our limit of a as it approaches from the right, same thing. One more quick example. No, maybe not so quick. We're going to use the definition to take a look at the limit as it approaches 0 from the positive side of the square root of x. Okay, so now we're going to guess the value for delta. Let there be a positive number. So a here is 0, the limit here is 0, so we want to find a delta such that x is greater than 0 but less than delta. So that means I'm going to take my function minus my 0, which is my limit, and that value is going to be less than epsilon. If I have this again, then I can see that it's minus 0. I can take that out. That just means the square root of x has to be less than epsilon. Square both sides of the inequality, and we will get that x has to be less than epsilon squared. So this suggests that we should choose delta equaling epsilon squared. So let's take a look. Given that we have, again, the value greater than 0 of epsilon, let the delta equal epsilon squared. X has to be bigger than 0 and less than the delta. That will give us the square root of x less than the square root of delta, which is equal to the square root of epsilon squared, which is E. So this will prove that our square root of x minus 0 is now less than epsilon. As a result, we can say, according to the definition, this shows that in fact the limit as x approaches 0 from the right of the square root of x is in fact 0. Now you can see this line right here I'm like, I think that's enough for this section. So this will be a shorter lesson today. And this is Doc. And we are day 3, lesson 7. And I'll see you in a bit for lesson 8.